Hi, everybody. This is Dr. Nigro with a screencast for Chem Calculations. This screencast is going to deal with how to use a rice chart as part of our equilibrium unit. All right, so a rice chart, it's really a table, or you can think of it as an organizer. And we use it to help calculate concentrations of reactants and products at equilibrium. All right, now you might say, well, Dr. Niger, we already did that. But that was if you knew KEQ and you knew the equilibrium amounts of all the components except for one. And in that case, you could plug an X in for the unknown, solve for X. This is a little more complicated because you're not given any information at equilibrium except for the KEQ value. What you are given are initial amounts of substances. So we're going to start with that initial amount. All right, so let's say that we have this reaction. So we have SO2 gas plus O2 gas reversibly forming SO3 gas. All right, so we check it. Oh, I put a 2 there already, so I'm going to need a 2 here. We have 4 oxygens. Yep, so we're all balanced. All right, so now underneath the reaction, we set up our rice chart. Now we start with R, all right, and R equals reaction in our rice. All right, underneath that, we have a row that's labeled I, and I is initial concentration. That's what we're going to fill in there. We have another row, which we label C. C is the change in concentration, and then we end with E, which are our equilibrium concentration. So that's what RICE stands for. Reaction, initial concentration, change in concentration, equilibrium amounts. All right, then I just separate it based on my substances. So I have a column for SO2, a column for O2, and a column for SO3. All right. Now, there are a couple things to keep in mind about the table. All right. The first thing is you need a balanced reaction. These coefficients are really important when using an equilibrium expression and within the rice chart. We'll talk about that in just a second. All right. You also need to pay attention to the state of matter. All right. So we need a balanced reaction. All right. We need to pay attention to the state. Remember, we can only use gases and aqueous solutions when we talk about KEQ. So that means if you have a substance in a reaction that's a liquid or a solid, then you can just ignore them in terms of your rice chart. You can just put a big squiggle or a big X in that column because they're going to be irrelevant. All right. All right. Also keep in mind all values that go into this chart, they must be molarity values. All right. So again, we use these 2 brackets to represent concentration. Same thing here. All right. When working with the chart, no negative values allowed. And you may ask, well, what does that mean? Well, we're going to talk about it. When we get to the equilibrium row, if you end up with a negative value in there, you've done something wrong mathematically. You have to go back and check. All right. All right. And then finally, right, you need to know the direction of the reaction. Now, it can be a little tricky. Sometimes, most of the time, all right, we try to work these problems where we start at the very beginning. So we have all reactants, no products. So we'll put zeros in for initial amounts. Some problems, however, give you initial values for all of your substances. And in that case, you're going to need to calculate Q first, compare it to KEQ to decide which direction the reaction is moving, all right, because that's going to influence our change row. All right, so let's say for a particular problem, just as my example, all right, I'm going to make up some numbers here, that the KEQ value for this particular reaction is 1.5, all right, and that at the beginning of the reaction, we have 0.25 molar SO2 and 0.25 molar O2 and no product. So this is the very beginning of the reaction. We're just putting our 2 reactants together. All right, so we fill in those values in our I row, our initial row. All right, now the change is the amount X that is used to produce product. And if we look at our coefficients, for every 2 molecules of SO3 produced, we're going to use 2 molecules of SO2. So we need a 2 in front of our X. All right. For O2 with no coefficient, we're just going to lose X amount of that O2. We're not going to lose it. It's going to be used to produce product. All right. Now, both of these are being used, so they are subtracted out. All right. And on our product side, X amount is being formed, and because we have a coefficient of 2, we have 2x. So we have minus 2x for 2SO2, minus x for O2, and plus 2x for SO3. All right, then we just take our I row and our C row and we add them together. So we end up with 0.25 minus 2x, 0.25 minus x, and then just 2x. And then those values will go into our KEQ expression, and we solve for x. All right. Now, I'm not going to do this exact one because I have a couple examples to work through, but that's basically how it works. You fill in your initial row with what you've been given. All right, so this row is usually given values from the problem. All right, your change row all right, we're going to use X for amount reacted or formed. All right, and keep in mind, I meant to move that guy. I'm going to slide this guy over here. Well, maybe I'll put it up here. There we go. All right. That the coefficients matter. All right. And then for this last row, the equilibrium row, you add the I and C rows. Oh, I should go back and say one thing. The negative sign is okay in the change row because that's what's being reacted, and the positive sign is what is being formed. All right. All right, so let's try one. All right, they look a little more complicated than they are, particularly once you get the hang of it. All right, so to study a hydrogen halide decomposition reaction, a researcher fills an evacuated 2-liter flask with 0.2 moles of HI gas, allowing the reaction to proceed to equilibrium at 453 degrees Celsius. At equilibrium, the concentration of HI is 0.078 molar. Calculate, the KEQ value. All right, so this is a little bit different. So we've got our reaction, we've got our initial amounts, we're going to have our change, and then we're going to have our equilibrium. All right, so let's think about what we know here. All right, we've been given the initial amount of HI. All right, so the concentration of HI initially is 0.2 moles of HI in 2 liters of space. All right, so we need molarity here. So we're going to first need to convert that to molarity. So 0.1 molar. So that can go here. All right, and it says nothing to us about the amounts of product. So we're going to assume that these are both 0. All right, for our change, it's going to be removing some of that HI because it's used to form product. So 2x. And then we'll be adding this amount X of H2 and this amount of I2. All right, if we add the two together, we get 0.1 molar minus 2x for HI, X, and X. All right, now you might say, well, Dr. Nigro, I don't know the KEQ value, so how will I find X? So we've got to look back in the problem. There's got to be some more information. And if you look right here, it tells us that at equilibrium, we have 0.078 molar of that HI remaining in the flask. So what that tells me is 0.1 molar minus 2x equals 0.078 molar. All right, so these types of problems, this can happen too, where you're actually given one of those amounts. So what I'm going to do is use this to solve for x. All right, so I end up with 2x equal to 0.022 molar. Divide both sides by 2. and I find that the change is 0.011 molar. All right, so this X is this value and this value. All right, so in reality, let me slide these down a little bit. This is 0.011 molar at equilibrium, and this is 0.011 molar at equilibrium. So I lose some of my HI to form these two products. All right, now I do know all of my equilibrium values, so I can use that to solve for KEQ. All right, so I'm going to write my expression. So I've got H2 times I2 divided by HI squared. All right, so there's my expression. Now I'm going to plug in my values, 0.011 for H2, 0.011 for I2, divided by 0.078 squared for HI. I plug that in my calculator and I find that my KEQ value at this temperature for this reaction is 0.02. All right. So the Rice chart was helpful here because it helps me organize what's going on. So it lets me recognize this equality right here. All right, and once I know what X is, then I can plug it in for my two products. Okay, so that's one way to use a Rice chart. All right, let's try this one. This one's a little bit different. Fuel engineers use the extent of the change from CO and H2O to CO2 and H2 to regulate the proportions of synthetic fuel mixtures. If 0.25 moles of CO and 0.25 moles of H2O are placed in a 125 milliliter flask at 900 Kelvin, what is the concentration of all species at equilibrium? The KEQ for this reaction is 1.56. All right, so for this problem, we're asked for the concentration of all four species at equilibrium if I know the starting amounts and the KEQ value. So this is definitely a place for a Rice chart. All right, so the reaction row, the initial amount row, the change row, and then the equilibrium row. All right, now for this one, we've got four species. All right, we're going to start by filling in what we know. All right, I've got 0.25 moles of CO and 0.25 moles of H2O. All right, so the molarity of CO is 0.25 moles divided by my volume, which is a milliliter, so I change it, 0.125 liters, and I find that I have 2 molar carbon monoxide in my flask. Now the amount of H2O is going to be the same because it's the same moles in that same volume, so we're going to have 2 molar there as well. All right, so we start by filling those two values in to our table. All right, we're told nothing about CO2 and H2, so we can assume we do not have any to start. All right, our change is going to be minus X, no coefficient for CO, so no extra number there, minus X for H2O, plus X, and plus X. All right, so at equilibrium, I'll have 2 molar minus X for my amount of CO, 2 molar minus X for my amount of H2O, and then X and X. All right, now, unlike the last problem, we don't know anything about these amounts. So we're not going to be able to solve for X with a given amount. Instead, we're going to need to use our KEQ expression. So let's write that. Products, CO2 times H2 over reactants, CO times H2O. So there's our expression. All right, we're going to set it equal to our KEQ value, which is 1.56. And then we're going to plug in this equilibrium row. So for the top, we have X times X over 2 molar minus X, 2 molar minus X. All right, now, I don't know if you're paying attention, but I can rewrite this. I can have 1.56 is equal to X squared divided by 2 molar minus X squared. All right, so this is a perfect square. We've got a square on the top and a square on the bottom, so I can fix that by taking the square root. Both of those squares are going to cancel, but I have to do it to both sides. All right, so when I do that, I end up with 1.25 is equal to X over 2 molar minus X. All right, so now I'm going to do some algebra. I'm going to multiply both sides by 2 molar minus X, and then I'm going to start to isolate. All right, so I end up with 2.5 molar minus 1.25 X equals X. Now I'm going to slide my 1.25 to the other side, and then I'm going to end up with 2.5 equals 2.25 times X. Solve for X, 1.11 molar. All right, so now I need to go back and look at each concentration. All right, so X is pretty straightforward. So this is 1.11 molar, 1.11 molar. Over here, I need to take that 2 molar and subtract out 1.11, so I get 0.89 molar, 0.89 molar. All right, and those are going to be my equilibrium amounts for each component within that reaction. All right, so watch out for these perfect squares. That's really handy when that happens. It makes your math a lot easier. All right, one last problem. Phosgene, which is COCl2, decomposes into carbon monoxide and chlorine gas according to the below reaction. Determine the concentration of all species at equilibrium, so that's going to be our goal, if the initial concentration of COCl2 is 0.5 molar. And then down below it gives us the KEQ value for this reaction. All right, so we've got RICE, nice chart. Set up our rows. After you do this a couple times, it becomes very straightforward. All right, now we're going to plug in what we know. So we know we have 0.5 molar of this. We haven't been given amounts of either product, so we'll assume they're 0. All right, everything's balanced, so we subtract out the change for the reactants and add it for the products. All right, and then we end up with 0.5 minus X, X, and X for equilibrium. All right, we're going to write our KEQ expression for this reaction. So we have CO times Cl2 all over COCl2. So there's our KEQ expression. All right, now we're going to plug in 8.3 times 10 to the negative 4. So that is a very small KEQ value, which means that we don't get a lot of product here. We've got a lot of reactants still at equilibrium. All right, and we're going to have X times X over 0.5 minus X. All right, now this problem is different than we saw before. We don't have a perfect square. All right, we can't take the square root of both sides because that's going to mess up our denominator of our KEQ expression. All right, now there are two different ways to solve this. There's the quadratic equation. So we could manipulate the reaction until we get a quadratic, and then we just use the quadratic equation to solve for A, B, and C. All right, not solve for A, B, and C, solve for X. All right. The other way, which is what we're going to start with, is we can make an assumption about what X is. All right. This value for KEQ is very small, which means the amount of change is going to be very small. We have a lot of reactants present at equilibrium, so it's not a lot of product being formed here. All right. So what we're going to assume is this X value is much smaller than 0.5, so that if we subtract it out, instead of getting like 0.32, we're going to get 0.4999998. All right, so it's going to be such a small amount that it won't even really impact the number. All right, when we do that, we can ignore it. So we rewrite our KEQ expression without that X subtracted out. So it looks like this. All right, now you can do this, but I'm going to show you at the end, you got to check it. All right, because this only works if X is less than 5% of what you're subtracting it away from. All right, if it's more than that, you got to go back and do the quadratic, I'm sorry to say. All right, now I'm going to finish. I'm going to manipulate my reaction, and I'm going to solve for X, and I find that X should be equal to 0.02 molar. So the change here gives me 0.02 molar of this product, 0.02 molar of this one. And here you're going to see I'm going to get 0.498, which isn't that big of a difference. Whoops, is that a 4? All right. Oh, sorry, I did that wrong. 0.48. All right, so it's not that big of a change for our product, but we need to check it. All right, so to check, all right, you take what x is, divide it by what you said it was much smaller than, and then multiply that by 100%. All right, when you do this, you should get 4%, which is less than your 5% limit. So you are allowed to use your assumption. All right. Now, it's very tempting to use the assumption all the time. All right. I always say that you should start out using the assumption, and when you get your answer, check it. But if your X value is more than 5% of what you're subtracting it out of, it is significant. Therefore, you have to go back and use the quadratic equation. Okay? All right. Let me know if you have any questions.